We are just close to it, also the second day of the conference, but not yet. It's my pleasure and honor in the same time to introduce the last keynote speaker of today. It is Dr. William Fowlkes. He's Vice President and responsible with analytics and workflow solutions at IPCOM in the United States, and we'll have a talk from his side about the application of artificial intelligence to creativity. Just a few words about Bill. He's an organizational leader with more than 35 years of experience in research, development, commercialization, and all aspects of the patent life cycle. Bill is currently developing new analytics and workflows for IPCOM, a software and services company that provides innovation tools for the intellectual property and engineering communities. He is a certified practitioner of trees, Taguchi methods for robust design, Six Sigma, and statistics. He is also the co-author of Engineering Methods for Robust Product Design, published in the well-known publishing house Addison Wesley. He's also inventor of a lot of US patents, 28 in number, and a Six Sigma black belt, and was a practicant of the very first SSBB certification program, led by Michael Harry from Motorola. Dr. Fowlkes then went and now is going to help to develop the first black belt program at the Eastman Kodak company. Bill has always had a passion for pushing the boundaries of process-driven innovation and quality improvement in his work. And yes, just these few words about the background of Bill say a lot. And I'm expecting to have a very interesting presentation. So now, Bill, the virtual floor is yours. I hope everything will work fine with the connectivity. So we'll work like that. We'll let Bill to handle the presentation. Otherwise, we'll take, if will be some troubles, the control from our side.
So I'm going to talk about the application of artificial intelligence to creativity. This is an applied use case. We've heard a lot of very interesting theoretical talks from the students today, and you'll see this is going to be a little bit different. Before we get into the details, just a little bit about IP.com. It's a company that's been around for over 20 years. They are we operate the first and largest data online prior art disclosure service, and we offer search tools such as Innovation Q that can search and retrieve data from more than 110 million documents, both patent and non-patent literature. And we also have professional-based patent services available. So you can go to our website and see more about us there. The agenda for today's talk, I'm going to review the basic principles of artificial intelligence first, and give a couple of examples to help illustrate how it really works, and then show you our work on applying artificial intelligence to innovation. So let's start off with a definition. Artificial intelligence can be thought of as intelligence demonstrated by machines, or often referred to as machine learning. And there are two areas I want to focus on today. First is natural language processing, which is of course of great interest to the analysis of patents, which is basically unstructured text-based data, but also pattern recognition in images, mainly to help illustrate what we are doing in text, because I think it's easier for people to comprehend an image than it is to understand what's going on in text, unless you really work on it. In both cases, there are patterns to be detected and to be analyzed, and thus intelligence could be achieved. But just to show you a very trivial example, or I shouldn't say trivial, a common example, is what you see in your viewfinder when you use a camera such as in your cell phone. Is you'll see these little boxes appear around each one of the faces, because the AI in the camera itself is able to detect patterns, and the pattern of two eyes, a nose, and a mouth is a very easily recognized pattern. And knowing that that's a preferred location for putting your focus on, the cameras do that analysis on the fly, and so that's an example of pattern recognition in imaging. Now, we're not going to get very far with artificial intelligence without representing knowledge, and this is what's referred to as an ontology. There's a example, simple example on the right, but it's basically the idea that databases can hold all sorts of information. It can hold certainly data, but it can also hold beliefs, information that's not necessarily data, but is representative of how people think. Expert know-how, common sense knowledge, all that information can be captured, represented, and manipulated through relational databases. It's basically a representation of what exists in an ontology. So now let me talk about learning algorithms, because really, as I said, we're talking about artificial intelligence, but it's often also referred to as machine learning. And there's actually a rich history of learning algorithms that have been applied to AI systems. And there's four major steps on the way that I want to summarize here. The first one is the simplest, which is referred to as symbolism, but it's basically rule-based formal logic. It's a hand-coded set of rules. It's if A is true, then B is true, or if A and B is true, then you can conclude C. Example of this is if an otherwise healthy adult has a fever, well, then they must have influenza. That's good. I'll talk about some of the pluses and minuses on the next slide, but a better approach that was developed afterwards was to use Bayesian inference, or statistical inference, and this reflects the reality of life, which is that things are not so black and white, where if A then B, but it's more like if A, well then you're more likely to have B. And so it's a probability-based set of rules. For example, if the current patient has a fever, then adjust the probability that they may have influenza. It's definitely close to the way people think, and it leads directly into the next step, which is really the first really big success in AI, which is the ability to model patterns and heuristics in the computer, and then applying statistics, be able to be very predictive. So now you're basing your inferences on the realization that there are a set of abstract patterns in the computer that are matching the conditions that are being presented. And so perhaps after, for example, after examining the records of patients known to have these symptoms, and these symptoms match the patient in front of you, well, then that patient is most likely has the same illness or has influenza like these other patients did. But all that pales in comparison to what's happening now with artificial neural networks. And the whole idea of the artificial neural network is kind of shown in the cartoon here. A real life network is a real life neuron in the brain. It basically is connected to other neurons, and a change in conditions in one neuron can be inputs to the neuron cell, and then that can in turn produce other outputs that go to other neurons in the brain. And scientists have learned to basically model that entire element, if you will, using mathematical equations for the relations between the input and the output, and connecting these all up in a network through software that can then analyze a number of situations and can be trained so that the weighting between the inputs and the outputs get adjusted over time to give better and better results. And we'll talk about that in the next couple of slides. So all these approaches have their challenges. The symbolism approach, the simplest one, is simply not extensible. Every single rule that comes into play needs to be hard coded into the software. And if you miss something, you can get the situation that was very common in the early days, that the AI has no common sense. It says, like, you know, it satisfied these rules, so this must be true, but it doesn't realize that there may be yet another rule that's not in the system that supersedes, and so it would make nonsensical recommendations sometimes. The statistical approach improved that performance, but it still suffers from the issue that you have to have every condition encoded, or else it's going to miss the situation entirely. The analogic or heuristic approach, this was really a huge success in simple systems, simple in the set of rules. For example, the IBM Deep Blue chess playing computers, you could basically hard code all of the rules of chess. There's a finite number of rules. There's almost an infinite number of positions on the chessboard, but there are clear rules for scoring, you know, the strength of a position, the threats on other of the pieces, and things like that. And so the scientists were able to encode the basic rules and encode rules for scoring the positions, and then the computer was able to go deep in very different promising threads and essentially outperform grandmasters ultimately. But again, that approach is a very computer intensive approach. And then along came neural networks, which, as I said, has been the most successful approach to date. It allows for really simple rules to be encoded. You don't even necessarily have to encode the strength of different positions, because the system can then be trained by playing through a game over and over and over again, or can be trained by presenting training data, and can actually teach itself to perform well according to whatever criteria you give it to perform towards. And the only real negative on the neural network is the last bullet there, which is it's often viewed as a black box. It makes people uncomfortable that they don't know what the neural network is doing, that they can't. Often the builders of the neural network can't even reverse engineer and explain exactly how the neural network achieved what it did. But you know, as is evidence from the AlphaGo computer that very quickly learned Go and then later learned chess, and again was able to perform at a level with grandmasters, but now do it in a much more computationally lean way, just indicates the power of the neural network. I mentioned learning or training. So there's a couple of typical approaches to machine learning. You probably heard people mention supervised learning several times in the last 2 days. This is where you basically can give the neural network input data, and you already know what the output result should be. For example, the classification of the data, and the system will essentially make its guesses and be told if it's right or wrong, and over time it will find the weightings that can produce more and more correct results, and so that's referred to as supervised training. I'll talk about the downside of that in a moment. Unsupervised training can basically find previously undetected patterns. You don't necessarily have to give it data that's already been classified by humans to give it the answer. It can literally find the answer for problems that only require grouping or classification. And as you'll see, for trees and for information retrieval, often unsupervised learning and the type of pattern matching that can be done with unsupervised learning is more than adequate to the system. The problem with supervised learning is that you need lots and lots of data that some humans have already curated and given the answers to. And I'll show an example of that in a moment. So this example here was provided by a colleague of mine in Rochester, New York, Professor Ray Patucha, and it basically talks about the training of image systems such as face recognition or what you see in Google Image Retrieve or Etsy and other websites that have image retrieval by images. That you have to be able to recognize what are the critical features. You have to localize what the critical features are in an image and to classify what those are. So it's kind of a two-step problem. And the way in which it's been done is with lots and lots of training data. And the thing is that the scientists have gotten together and they've produced databases of training data for situations such as this for academics to use, for students to use, and ImageNet is one of those examples here. It's basically it's built on the same hierarchy as WordNet, so it's got a rich lexicon of words, nouns, verbs, definitions, and all the like. And here in this case, these images have already been classified. Where they're by whether it's a mammal and a placental and a carnivore and a canine, so this image here, dog, working dog, whatever multiple classification given image is in this database. And so this forms a very rich source of already prepared data for supervised training. So Patucha's group used this data. It also used data from Pascal VOC, which had a whole nother set of both classifications and also localization to basically do the overall training of their system. And their students were able to demonstrate, really good results using pre-training with the ImageNet data and then fine-tuning using the Pascal. It's not that I want to go into a whole big thing with image classification. I want to use this as an example for you to understand that it's a real challenge if you don't have the data, but if you do have the data, it's a real opportunity. And we'll talk about that in a moment as we shift over to text-based data. Let's just say a little bit more about that neural net. So here's an example of a practical neural net that's used for autoencoding. That's the ability to take an image, to basically use the neural network and set the neural network with a structure such that you reduce the dimensionality. The initial input will have to have, each pixel in the image will provide data to the network. But as we know, like you think about a sky, it's all the same color over a broad region. So it doesn't really need the full dimensionality of every single pixel, even though that's how the image starts. And so autoencoders can greatly reduce the dimensionality of the image, which is shown here in the middle with the compressed image. And then reversing that to decode can produce a near perfect replica. I mean, if you're really critical and it's a lossy system, you'll see some differences, and this example does show that. But nobody would have any problem recognizing that the dog on the right is the same as the dog on the left, even in that situation. And the opportunity here is that in its compressed state, you have all the information that you need, but you're working with much, much less data. So it makes it much more efficient to sift through great quantities of information looking for matches if you work with the compressed image. And this is what people were saying. Somebody was saying in one of the talks today or yesterday, I mean, that that they were able to reduce the dimensionality of a data set of text down to just 300, essentially 300 factors, and then be able to do retrieval. We use a little less than that, but we do the same approach, and I'll talk about that in a moment when I talk about our system. So I'm going to go on to the application. Are there any questions at this point? I'd be happy to pause here and talk a little bit more about artificial intelligence in general. Okay, then I'll continue. So the semantic gist is our primary AI that IP.com uses for processing text documents. Initially, it was all patents, and now we do non-patent literature as well. It's still all technical-based literature, and our AI has basically two models that we use. We use a statistical language model, the next slide, and we use a deep learning neural network, which is very similar to what I just showed you. And these tools together are the engine that basically underlies our current product, Innovation Q, and our new product, Aubrey, which I'll be showing you towards the end of this talk. So the statistical language model is basically constructed from a collection of documents. Approaches that can be used is a simple bag of words. Just count out all the words in a document, and if two documents have a similar distribution of words, and then they're probably have some similarity between them. But the frequency of the words can be used to spot keywords, as we would know readily, because we use stop words to weed them out. Very frequently seen words that are fairly short, like the, and. These don't carry any useful information and can be eliminated. But at the same token, words that appear maybe only once or twice in an entire corpora of data are probably also not that important. Certainly not going to be that useful for pattern matching. And so we can use, keyword spotting, co-occurrence frequencies, and even probabilistic models that help the system to interpret a word in the context of the words around it, so that that the word blockchain in a document that's all about ships and anchors and sea would have a very different meaning than the word blockchain in a document that talks about banks and finances and things like that. And so so probabilistic models and a statistical language model helps to sort that out. The other tool is the autoencoder, which works really exactly the same as it does for images. And in fact, our CTO likes to describe it as, we take all the documents in the world and we basically figure out the colors that inform those documents. And what he's talking about is the compressed feature vector, which in our case is about half of the example I said with 300, and so those 150 or so different colors, if you will, and how strong each color is depending upon the words in the document, can then be used as in a pattern matching algorithm to bring back other words that have a similar distribution of colors, if you will. And so what we're really using is we're transforming text into vectors, into a multi-dimensional vector, and then we're using cosine similarity approaches to find the other documents with a similar vector to be more mathematical about it. So does it work? Well, the two key measures in information retrieval are precision and recall. Precision talking about did you find all of the relevant documents in the corpora when you did a retrieval, and recall saying I might have gotten that backwards here. Yes, I did. So recall being the ability to find all the relevant documents, and then precision asks, well, but how much junk did you pull in at the same time? Did you pull in only relevant documents, or did you pull in relevant documents and a lot of non-relevant stuff? So you want to balance that out, because you don't want to retrieve everything and have low precision but high recall, but you don't want to retrieve almost nothing and have very good precision but miss important documents with poor recall. So how do we do? Well, they told me I can't tell you, but I not quantitatively, but I can tell you that our performance in this measure is very high. But what I can show you is an example to illustrate how well we do. And to do this, I took our product Innovation Q. I gave it a very simple query: vaccine for coronavirus. So it's only 4 words, one of which is a stop word, and we'll get thrown out anyway. And you can see the results here. Each one of these dots represents one or more patents that have been retrieved. And the words are keywords that were extracted from those documents. And you can see that with just 3 essential words, we brought back documents to talk about pandemics and prevention, chicken, which is a medium that's used for creating vaccines, cloning, which is another technique that's using for vaccines, SAR, which was another major target in the past of successful elimination with vaccines. So you can see from the keywords that are associated with the documents that were retrieved with a very simple query that in fact we are bringing back the information that we're seeking. So let me move on to the main topic, which is, can we apply artificial intelligence to innovation? Can AI solve difficult problems? Can AI replace human ingenuity? Well, for those of you who have been working in artificial intelligence, you'll recognize what I'm going to say next, because that's probably the wrong question. The real question is, how can AI assist engineers to creatively solve problems? The way things are shaking out in industry right now is more and more often we're finding that AI is not a thing that replaces humans. It's a thing that augments human intelligence. It's a thing that assists humans to do their job, but to do them better. So nobody's saying that diagnostic software is going to replace your doctor. You're still going to have your doctor. You're still going to go and talk to your doctor. But then if the doctor can use the AI to do a much better job of diagnostics, that makes a lot of sense. And similarly, it's our expectation that AI is ready and able to assist engineers to creatively solve problems. And I'm going to show you our example, our foray into that field. So if you think about the traditional trees process, where a perceived problem, you start with a perceived problem, and you traditionally before trees, or for people that are not users or experts, practitioners, they'll attempt to go directly to their solution by some kind of brainstorming process. It's what people do. It's what engineers do to solve problems. But Altshuler and his colleagues and people that have developed trees have shown that a much better approach is to first figure out what is the underlying problem, the real problem. Do the functional analysis to reveal the causes, to reveal the conflicts, and then find the standard problems in the tree's corpora that represents that real problem. And that allows you to find the standard solutions, and then through some type of analogic thinking, try to create solutions to your actual system that are related to the standard solutions. So that's the state of the art today. What we have built in our tool called Augmented Brainstorming, or Aubrey for short, is an assistant that can take care of all the parts that are in the dotted line. So it will help you to describe your perceived problem. It will then use the AI and the pattern matching to find the best standard problem representation and standard solutions And then the engineer, what the engineer still has to do, and we still want them to do, is to come up with the concrete solutions to their problems based upon the standard solutions or suggestions that are presented by the software. So I'm going to give you a very brief look at look-see into Aubrey, and tomorrow we're running a workshop where a number of people are going to get to actually try it and use it. Stellian has a copy; he's been using it, and certainly if you contact me, I left my contact information, or if you can participate in tomorrow's workshop, you can actually play with the software. But basically, we have 2 engineering analyses to help the engineers do a better job of describing their problem. So we have cause and effect, and we have system improvement. So the problem analysis approaches. So cause and effect. This starts with the simple problem statement. Tell the software what your problem is, and then describe using the 5 whys approach, what's the root cause for the problem? In other words, if you have a problem, why do you have that problem? Why did that occur? Well, tell me now, why did that occur? And basically up to 5 times, answer the question, and you'll have a pretty good analysis of both your problem and the events or issues that could lead up to that problem. And that's a good problem description. But we recognize that in business, not all innovative needs are based upon known problems. Sometimes the system's working just fine, but because of competitive pressure or marketing request or whatever, there's a desire to improve the system. So in this case, we ask the engineer to describe the system and do a good description, including the elements in the system and how they interact and the system's purpose, what useful functions are produced by the system, and then tell us briefly what improvement you're looking for. So, so for example, in the cause and effect analysis in the software, we have 1 box for describe your problem, and then we have 5 boxes for tell us, the events that can cause the current problem and why did that occur and why did that occur and why did that occur. In the case of a system improvement, we have 1 box for describing the system, and then we have a 2nd box for telling us specifically what do you want to improve. And because the system description is important, we do put some constraints. You can't do like a 5-word description of your problem because we know that will be inadequate. So we require at least 20 words to adequately describe your system. And really, that's barely adequate. I'll illustrate this with an example. So for example, a system description that the novel coronavirus infects lungs quickly, the breakdown of delicate tissue and resulting in extreme shortness of breath. A ventilator is a machine that provides mechanical ventilation by moving breathable air in and out of the lungs to deliver breaths to a patient who is physically unable to breathe or is breathing insufficiently. Modern ventilators are computerized microprocessor controlled machines. So you see, I've got all the elements in there, the patient, the lungs, the air, the machine, the controller in the description. And then the question is can we develop a better ventilator for COVID-19 patients? So that's the extent of the input that we ask engineers to provide. And then what the system does is the system produces inventive suggestions applying Tree's inventive principles, using the GIST AI, our semantic GIST, to figure out what are the inventive principles that are most likely to be useful. In other words, we don't use the contradiction table. We don't ask the engineers to try to figure out what the contradiction is and then go to a table to find the 4 most likely to be useful inventive principles. Instead, the software uses its pattern recognition and artificial intelligence, its semantic AI capabilities to find to basically rank order the inventive principles and put the most likely to be useful ones at top, given the nature of the problem. At the same time, because we can and we do, we use a search of the U.S. patent applications to provide a functional concepts list of suggestions, and you'll see that in a moment here. And this takes the place. What this does is it provides the user some idea of what's been tried before, what's worked before, has worked well enough that somebody created a patent application. In trees lingo, you can think of that almost as an effects database being applied to the problem. So the way it looks in the software is like this. On the left side here, you can see the inventive principles. This is the first of many. It's not shown here, but there's a next button that would then walk through the different inventive principles. We identify which principle it is so that the trees experts can correlate this. We provide a plain English description of the principles. And here's the key thing. Because of our semantic analysis, we can actually bring back related terms at the bottom here, like lung, respiratory, treatment, breathing, gas, disease. You'll notice that these terms go beyond what was in the problem description, because these terms actually come from the highly relevant patents that are returned after the query is done, and then those are the keywords are extracted from that. And you can look at that related terms and think of it as it's like a list of system resources that are likely to be available. And if they're not available, you probably should think about engineering your system to make them available, because based upon the literature, that's what other people are doing. So we actually marry these words directly into the abstract into the inventive principle, where normally you would have an abstract statement like divide the objects into parts. Here we'll say specifically divide the airway into parts. We provide a simple explanation, and we provide an example, often with a link out to a patent or Wikipedia to further illustrate it. And then on the right here, you can see the functional concepts, where we are basically, as I said, retrieving the title and abstracts from a number of patents. We only show a partial abstract because it's not like you're supposed to read the patent and analyze it and everything to brainstorm. Usually just seeing the first 30 or 40 words is enough to get a feel for what the patent's about and can inspire your thinking and maybe lead to a new idea. Like if you look at the first example here, hydrogravitational method and device for lung refurbishment, and it talks about the patient is rotated in specific 3D orientations. Now, we all know that ventilation has been saving people's lives when they get COVID, but how many weeks or months did it take for the doctors to figure out that the ventilation would work better if they turned the patient over face down? It's the first result that came up from this search engine. All right, so I'm on my last slide here. So I want to talk about AI and trees. So, and ask the question, was Altshuler simply ahead of his time? You know, on the left here is all the things that Altshuler did, and having gone through kind of the basic history and fundamentals of artificial intelligence, we can begin to recognize just how close he was. And if only he had had the computer power that we have now, perhaps studying millions of patents, we would have called that supervised learning. And extracting abstract problems and solutions, well, that's his analogical knowledge representation. And the inventive principles table, well, there's your statistic heuristics. He basically used this some statistical analysis to decide for each intersection which patent should go into that box. The algorithm of inventive problem solving, or RIS, is essentially analogic or heuristic algorithms. So we have almost all the pieces of AI here already. The table of effects is basically the knowledge ontology of physical and chemical and mathematical effects that can be useful for problem solving. And the only thing that's missing here, which I mark as future, because I'm not sure that he did anything like this, nor would he have been able to conceive of it, but you think about the neural networks that I described earlier and what we can do now, and you think about the research that we heard about in the last 2 days. Here's the challenge for us going forward as a community, is to figure out how to use the patents as training data. The neural networks works as a system to analyze that data, and perhaps we can get even closer to the day when the artificial intelligence really can be creative and solve problems. So that's the end of my talk. And if there's any questions, I'll be happy to entertain them.
Thank you very much, Bill. I think we already have one question. I think somebody raised up the hand, so please ask the question.
Yes, thank you for your presentation. I have a question. For the similarity between the patents and your keywords that you write, what similarity did you use?
I'm not sure. Say that again and expand a little more on.
You extract some. Do you use some encoder to extract something from the text, and then use the similarity between the patents and the problem that you described?
I understand. Yeah.
So what's the similarity? But
so we use the encoder to round up the patents that have similar content, but then we use the natural language processing, the statistical language models, I mean, to further narrow it down and to prioritize the patents that are returned by the neural net. So we actually do a balance of two approaches to get the optimum results.
Okay. And for your semantic map, I was wondering, how did you draft that?
Yes. So that was drawn by Innovation Q. That's something that's built into Innovation Q. And by the way, both are two-factor approach. That is, say, the neural network and the statistical language model, and the visualization of the results from a multi-dimensional universe down to 2 dimensions, which is what you basically see in the semantic map. Both of these have been patented, and the details are available. And if you send me a note, I'll be happy to send you the reference numbers, the doc IDs. So that's basically what's done there. Is we basically we retrieved that was 15. That map represented the first 1,500 results or most relevant results from the patent database. And then we do a projection onto 2 dimensions from the multi-dimension universe. And then we use the keywords as you project the documents you project through to get down to just 2 dimensions for the map. You pick up the keywords from those from the statistical language model and add the keywords to the map. So that's basically how that's produced.
Thank you. The next question, we have still 2 colleagues with hands raised up. So please, one of you, Jerry.
Hello?
Yes.
Thank you for the very illustrative and very nice presentation about AI. There is some effort lately about black box versus explainable AI. I would appreciate your comment on this.
Yeah, so it's very interesting because you would think people would be all about results, but there is a real tangible, it's in your gut comfort level that if the computer produces results and you don't understand it, there's this uncanny feeling. Now in the film industry, that term comes from the film industry when they use AI and computer graphics to produce artificial humans on screen, and they're close, but they're not perfect. People get very uncomfortable. They see it and they see that it's not real, and it's acting like it's real, but it's not real, and they get very uncomfortable with that. And it has to be almost like so perfect that you absolutely can't tell for it to be accepted to people. It's not exactly the same, the black box effect, but it is an analogy to that people who use AI tools like neural networks that can't understand the internal workings, they have a gut discomfort with that. So if there is a new thing, and I haven't heard this yet, but if there is a new technique for constructing at the same level of performance neural networks, but to be able to understand what it's doing, that would be great. Just to pick a concrete example, it would be wonderful if when we reduce a pattern dimensionality from its original, thousands of words down to, here are the 150 colors. If we could put a label on each one of those colors and say, it's there because of this, it's there because of this, it's there. No, the label is XYZ 3, 4, 5, 6, 7. And when I ask the engineers, well, what does that mean? They can't tell me.
And what is, in your opinion, the ultimate state of using AI? We are somehow afraid of the answer. Why is that? Because computer said so. So what will be in the future? You are expert.
I think that there's going to be a convergence of young people that were brought up on it and never knew anything different, and better performance. And this discomfort is going to be a transient thing that's going to go away.
All we have to do is just die.
Hey,
I mean, the old guys, yeah? Thank you.
You got it. Thank you.
Great. Next question, please.
Hello, thank you for your presentation. It was really nice. I have one question for initial analysis part, cause analysis. Could I know, please, which method did you exactly use for this phase of inventive design? Because you speak about cause analysis, but I didn't understand exactly which method did you use exactly.
Yes. So it's a known Six Sigma approach to do root cause analysis. I think it's probably similar to what other people refer to as RCA, root cause analysis. But the analogy that we use is the 5 whys. So it's that asking why. We actually use that to prompt the users to give us the useful information. We then take all their words and mash them together into a single query. And the same thing with the system improvement. We basically ask 2 questions and we give some guidance for how to describe your system well. And then we mash the system description and the improvement together and run a query. We were concerned. This does bring up issues of ease of use and training. But so far in the beta testing, the engineers have had no trouble providing good queries using the guidelines that we've created. So there's really no magic. It's entirely what's there. Boxes that basically give you some instructions as to what to put into the box.
Okay, thank you.
Sure.
Thank you. Oleg, please. You have a question, yes?
Yes. Thank you very much. First of all, it was very educating. As I understand, the result which artificial intelligence will give you should depend on the information which it had at the input. And when we are looking for, let's say, recommendations for some solution, we maybe need to make sure that the information which was fed to the artificial intelligence belong to the right domain.
Mm-hmm.
Is it correct?
Yes, yes.
How do you make sure you don't know what the solution is? How do you make sure that you give the right information for the AI to study?
Yeah, no, that's a great question. So the patent data is very solution oriented, and it's pretty easy because there's technology classification, CPC codes applied to patents. There's the descriptions in the patents. It's pretty easy to retrieve, chemistry patents for chemistry related problems, mechanical patents for mechanical related problems, electrical for electrical. That part is fairly simple. We further found that the patent applications have much more, if you will, unfiltered information about the solutions, because it actually precedes the whole process of producing a patent in which the examiner may influence what's in the patent, the final patent. So the patent application is more like raw data. So we found the patent application is the best. Non-patent literature is actually not as good, although customers want to see it, because often it's more like survey stuff or it's a letter that's very, very brief, and it's harder to characterize because a well-written patent will include background information about the subject matter as well as the problem description and the solution. So I think it's the fact that we're working primarily with patent data, which is so technical and problem-oriented, that this works. I feel that if we weren't a patent data-based source of information, it probably wouldn't work as well.
Thank you very much. I understand.
Okay, thank you. We have 2 new questions. So in the order of raising the hand, so please. Also the third one, so we'll come up. So please.
Okay, not a problem.
Who's next? Yes.
It is me?
Yes,
sure.
Please.
Okay, my question is the following about patents. Your AI technologies, I suppose, are also capable to automatically produce patents. What would be if you? I have no idea how many patents your engines can produce per day. What will happen if you generate such patents and flood the patent offices with them? So this is the end of the patent world at all?
So that's a problem for a future date. People have speculated whether or not patent offices will accept innovations that are produced directly by machine. In fact, I believe there's case law, but I'm not a lawyer, and I'm not going to get into that. But I believe that that's already been discussed at least in law journals and things like that. If you noticed in my diagram with the green line, we still have the human going from the suggestions now. We call them suggestions to broaden it to include both the functional concepts and the inventive principles, to go from the suggestions to the actual solutions. So you still have to be involved in the critical creative step. So the patent, there will be no doubt that the inventor of the patent is the human that's using the software, but is making the final decisions or making the final description, if you will, of the invention that could solve problems. When we get to the point that the AI can even do that, we're going to have a huge court case, and that will get resolved in the court of law, I believe. But we're not quite there yet.
I have no idea this, because first, Valsurikov is working on this already 2 years with this team. Second, TRIS has more or less, it is for patent avoidance. They use TRIS already more or less to write structured patents, because we have that, we have this contradiction, we have it solved. So one can generate such paper versions of this, and then Bill Fowler can fail this as a patent claim, and no one will know that it's a machine generated and not generated by Bill Fowler or by Valsurikov or by what else. So even that the internet is full of social bots, machines that do something that looks like human. So your optimism that this is for future, I do not share.
No, you're right. I think it is still a future problem, but the future is very close. I do agree with that. I will say this, however, I don't know if you know this, but at least in the US, and I'm sure it's true in Europe as well, both the inventors and the lawyers have to sign documents attesting that they are the inventor, and patents can be challenged by a competitor on the basis of incorrect inventorship. So that's why this is going to get tested in a court of law, because somebody's going to do that They're going to get the patents. They're not going to acknowledge how they did it, but some competitor is going to know enough through competitive intelligence that they're going to bring this up in a court of law, and the judges will decide. And you're right. It might not be 20 years from now. It might not be 10 years from now. It might be next year that happens.
Yeah, thank you. Just somebody mentioned colleague in the chat, but indeed, a few years ago in New York was sold a painting, 100% done by computer with adversarial generative networks, and yeah, I think about $400,000, something like this around. So
right,
yeah,
and deep fake videos.
Yeah, deep fake videos. Yeah, so
where they're past the uncanny are going to be a huge political problem. And again, the future is very close.
Yeah. So we have a next question from Professor Nagakawa, from Toru Nagakawa from Japan. So please, Professor.
Toro-san, thank you. Yeah, nice to hear from you.
Thank you very much. A nice presentation. As you know, I've been working for making catalogs of tree sites, and some people say that instead of writing introductions of sites by human, we should just use AI. That's simpler. Somebody says so, but I can't believe it, because there are a lot of pages each website has, and I don't think the current AI can summarize each website properly, distinguish some website and other in a proper way. I can't believe that kind of thing can be done for several more years in future. We should write an introduction of 5 lines or 10 lines is very difficult, and I think so.
Okay.
Nevertheless, we have to embrace this. Yeah. So please, Bill, if you have a comment on it.
Thank you for the comment, and you know, somebody already said I'm optimistic. I am optimistic that AI will find its place assisting us, not replacing us, but we'll see.
Let's see. Thank you. Thank you. We have from Igor another question, please, Igor.
That's fine. Yeah. Questions are the best part.
Igor, can you? We cannot hear you.
Unmute, Igor.
Yeah, please unmute your mic. But
me? No, is that me? I'm not Igor.
That's better.
No, I'm not Igor. I'm Shin.
Okay.
Is that my turn now?
Yeah, you can do this.
Please.
Yeah. Okay. Really, thanks for your. Actually, I have a question. How do you evaluate ego? For example, like your money. You evaluate it's the really solution for your problem.
Okay, we have to stop because two persons spoke on the same time. So
there was a crazy echo. There was a crazy echo, Shin.
So Shin, you have to say, and Igor, then you will continue. So Shin, please say again. Please answer the question again.
Okay.
Ask the question again.
I can ask. Okay. Thank you. Really, thank you.
Much better.
I want to know now. Actually, how did you evaluate your model's performance? Like, your model could give a solution for the target problem, and how could you know it's the really solution for the target problem? Do you use some methods to show this?
Yeah. So to be honest, Shin, we're depending upon our human testers to tell us if it is giving them good ideas. Long term, we're going to know through the number of successful ideas that are generated and patents that are generated, and medium term by the market acceptance of the product. I don't really have, and this is a good research problem. If somebody has some suggestions, I would love to have an offline conversation. I don't really have a solution yet for how to quantitatively measure the applicability of the suggestions, both the functional concepts and the inventive principles that are generated by the tool. So that's an open issue, and if you or anybody else has some ideas and would like to have a discussion about it, I'd welcome that, because that would be much better than what we are depending upon, which is essentially word of mouth and market acceptance.
Okay, thank you, Riley. Thank you.
Wait, Stellian, you've used it. Is it giving results that are on target and that are useful?
Yeah, so actually, is that what you guess my intention to intervene? Yeah, I have tested the platform, and I was really curious to see how the system can inspire me for some challenging problems, and I had a positive feedback. Definitely, it's an involvement of you as, let's say, the person that interact with the system. So we cannot still say that I just ask the system, I like to have a solution for something, and the solution will appear. As it was mentioned, you need to interact. So depends very much of what you introduce, how well you set up your problem. Okay, assisted by 5 whys, for example, or other patterns. Nevertheless, you are encouraged to take some of the ideas and introduce into the system. Maybe you can use this to reiterate, but at a point, this is my feeling. People need to be assisted. They feel more comfortable if they have something that collects from a broad knowledge base, something, and bring very fast to them. And this is something that I think it's a catch for using these capabilities. Nevertheless, research and science is in with this job to make system more performance, to prove different algorithms that are reliable. But from the innovation side, I would say that we have, and this is maybe something good in the United States, that in the United States I see this fast application of something that it's valid or has a certain level of viability, not waiting 100 years till the system is perfect. And for the progress of humankind, I think something very valuable as an approach. And I salute from this perspective also the presentation. As was mentioned by my previous colleagues, it was very educative for many of us in terms of having this capacity to explain in a few slides the basic guidelines or principles of non-supervised artificial intelligence. So this is more important. Yeah, this is my perspective.
Thanks.
And I really encourage, and that was also one of the goals introducing this keynote presentation, to encourage the TRIS community that we have to embrace the technology. We have to embrace the technology because we have a huge resource around us, generated by humans, definitely by humans, with assisted a long time with the technology, but definitely we have to use it. Watson from IBM, yeah, is something that, yeah, they were 30 years to build up Watson, and I have even had a chance to interact with Watson from IBM, for example, I ate some food recommended by Watson, which was incredible good. So nobody would be able to say what was behind, but I would say that was excellent. More question, or shall we end this session? Okay, I think, Bill, we have
Well,
to.
thank you very much, Stellian.
Yes, it was a great
really,
pleasure having you.
Appreciate the opportunity.
And I think it was a very inspirational talk for the trees community and we hope in the next editions of ETRA Trees Future Conference to have more papers with AI and trees. So thank you very much once again. Thank you to all. And yeah, if some of you would like to continue discussion in the private channels, you are welcome. Nevertheless, I'd just like to highlight an important thing. Today, the October 15 is the birthday of Altshuler. And I would like to highlight this because, yeah, just a respect for the man who at least made a paradigm shift in many respects in terms of innovation and how we speed up the innovations in the world. So, yeah, I just wanted to point out this. So with this, I wish you a good day. Depends of the time you have at home. I think in Korea it's close to go to bed. In the United States is maybe the morning.
Right.
But nevertheless, Bill, I saw you very active in the midnight, very early in the day to attend the other session. So thank you for being involved with us in this conference. Thank you once again to everybody, and see you tomorrow with other inspirational and high quality presentations. So we'll have another 2 keynote speeches tomorrow. Thank you, and have a good day.